The title of this notes is Derivative of a Function, and the outcome is to be able to define a derivative, especially its notation, and to describe a derivative algebraically, graphically, numerically, and verbally. So a derivative represents a change. How quickly is a function changing? And we've been talking about finding the slope of a tangent line. That is the derivative. That tangent line represents how quickly a graph is changing at that given point. So we have a definition for a derivative, and I hope this looks familiar. We have notation here. This is read f prime of x. And that just means the derivative of f. So how quickly is f changing? And the way we calculate that is we have the limit as h approaches 0 of, and then this should look familiar. This is our difference quotient. So we can use this definition to find the derivative of f of x equals x cubed. So remember, derivative is just the change or the slope. Slope and change mean the same thing. Up until now, we found the slope of a tangent line when you're given a point. But you'll notice in this example, we're not given a point. What we're going to come up with instead is an equation that will give us the slope of x cubed at any point. So we're going to use this definition. So f prime of x equals the limit as h approaches 0 of the difference quotient. Right now I'm just copying the definition. And to find the derivative of this particular function, we're going to substitute x plus h into the function. So notice we don't have a number for x. So instead of x cubed, we're going to put x plus h into that function. So it will be x plus h cubed. And then the second term will be minus f of x, so just minus the function, all over h. So there's that difference quotient. It's okay that we don't have a value for x. We're going to go ahead and simplify as much as possible anyways. So first thing we need to do is we need to simplify this x plus h cubed right here. So we are going to have to FOIL. And we're actually going to have to FOIL twice. I'm going to do this work in a different color. You should be doing this work off to the side. So x plus h cubed means x plus h times x plus h times x plus h. So first I'm going to multiply these. You can FOIL, box, distribute, whatever makes sense to you. So those are the first two. Then I'm going to multiply that by x plus h. So again, you can distribute or box, whatever makes sense to you. So x squared times x is x cubed. 2hx times x is 2hx squared. And then h squared times x is just h squared x. Now I'm going to repeat. I'm going to distribute those terms to the h. X squared times h is just hx squared. And then 2hx times h is 2h squared x. And then lastly, h squared times h is h cubed. And I have a couple of terms in here. I have hx squared, hx squared. So there's a total of 3 hx squareds. I cross them off as I use them. And I also have an h squared x and 2 more h squared x. So there's 3 of those. And then there's the h cubed term. So all of this was x plus h cubed. All of that. So that was my work to figure out what that is. So now I'm back to actually solving the derivative. So So the limit as h approaches 0 of, in that first term, x plus h cubed, we just did all that work to find out it's x cubed plus 3hx squared plus 3h squared x plus h cubed. And then the difference quotient keeps going. Just slide this over here. So we have this first part, and then we're going to have minus x cubed all over h. And just like we've been practicing with our limits, if we were to substitute 0 in right now, we'd get 0 over 0, the indeterminate form. But notice I can apply some algebra skills. First of all, in the numerator, x cubed minus x cubed cancels out. And then with the terms that are remaining, notice how every single term has an h, so that is a GCF that you now want to factor out. So I factored in h out of every single term, and I can divide h by h as 1. So now I have the limit as h approaches 0 of 3x squared plus 3hx plus h squared. So now I can directly substitute 0 in for h. If I put 0 in here, 3 times 0 times x goes to 0. 0 squared goes to 0. So this all cancels out. It goes to 0. So that means that the derivative is 3x squared. So now if I wanted to say, okay, well, what's the derivative at 1? I could just put 1 into this equation instead of doing all of this work with 1. That's one definition of a derivative. There is actually another one. Oh, before I show you the other one, let's just look at two former AP questions. So in the first one, if f of x equals e to the x, which of the following is equal to f prime of e? So here you're just being asked to put this into that notation. The limit as h approaches 0 of f of x plus h minus f of x all over h. And you actually have an x value this time. It's e. So you are doing e for those x's. So you then get the limit as h approaches 0, and the function is e to the x power, but you're going to replace the input with e plus h. And then f of e would be e to the e all over h. And you're going to look, and I can see right away, I already have my answer. This is choice E. Take a look at the next one. It's not answerable yet, but we can still talk about it. What is the limit as h approaches 0 of 8 times 1/2 plus h to the 8th power minus 8 times 1/2 to the 8th power over h? So notice this is your f of x plus h minus f of x. So if I ignore what's in here, I hope you can see that the function is 8x to the 8th power, and the x value is 1/2. So this question is really saying, what is the derivative of this function at 1/2? When x is 1/2. So I'm actually not even going to write x, I'm going to write 1/2. And there's a way to calculate that, so we're not going to answer it. But you need to know that that's what it's actually asking. It's actually asking for the derivative at 1/2. Okay, here's your other definition of derivative. This one is when you just want the derivative at a point. In the last chapter, we used this one for the derivative at a point. It's the same one that's x. It's the same one you saw on the first slide, so you don't need to rewrite it. But I gave you x. This time I'm giving you the x value, I'm calling it a. So you have a couple options. You can either write this as a. That's terrible handwriting. I'm just rewriting so you can perhaps read that. So one of the things you can do is you can plug in a for h. Or, this might be even shorter, you can use this definition. I hope you're seeing slope here. M equals y2 minus y1 over x2 minus x1, where x2, y2, we're using the symbol x, and x1, y1, we're using the symbol a. So it's just a slope. Derivative is just slope. If you can remember that, you're going to get through half of that test. So here's some notation for derivative. So you have a function y equals f of x, so there's lots of different notation. This first one is f prime. It's that there's an apostrophe there. F prime, that's the derivative. You can also just use y prime, so whether you're using y or f of x for your function. You can also use dy dx. That's how you say it, dy dx. And that means the derivative of y with respect to x. If you're using f instead of y, you can say df dx. Or this last one is read d dx f of x. So all of those different notations all mean derivative. You don't have to use any particular notation. I'll tell you the two that you're going to see the most are this one and this one. Don't need to memorize them, just need to know whenever you see that it's asking you for a derivative. All right, so the last thing we're going to put in these notes is we're going to talk about the graphs of f and f prime. I'm just going to draw an arbitrary function and call it f. Graph of f. From that graph of f, I could now graph its derivative. Remember, a derivative is just a slope. So to graph a derivative, I'm going to think about tangent lines. So for example, let me put a up here. Let's call that point A and point B, just so that we have something to match our graphs to. Notice that at point A, if I were to draw the tangent line, it's a horizontal line that has a slope of 0. So the derivative at A is 0. So if this over here is a graph of f of x, the derivative at A is 0. On the left side of A, any tangent line that I draw is going to have a positive slope. But those positive slopes are going to get less and less steep as I approach 0. So it's a positive number that's decreasing to get to 0. So maybe that's the derivative. Once I'm on the other side of A, those tangent lines have a negative slope. And they get steeper and steeper until about halfway between A and B, and they start to slow down again. And at B, I have another horizontal tangent. So over here, I have negative slopes that are getting more and more negative, and then they start twisting back to 0. So they get back to 0 by the time I get to B. And then on the right side of B, these tangent lines have positive slope, and they're getting steeper and steeper and steeper, and they're going to increase forever and ever. So I have positive numbers that are going up forever and ever and ever. So there's a graph of f compared to its graph of f prime. We're going to practice this in class. This is where your notes stop. Go ahead and draw your line and come into class ready to talk about derivatives.